All right, hello students. This is Professor Barish, and I wanted to mention that this particular presentation is replacing the class that we normally have, would have normally had on Wednesday, November 17th. Right, so this is the class that would have been at that point, since I'll be away. And so we'll be going over today in our Locke textbook, section 6.1, and in particular, confidence intervals. All right, there's actually three sections in 6.1. There's one regarding the distribution of a proportion, which we will go over first, actually, before we talk about confidence intervals. And then there's, of course, the confidence intervals, and then the hypothesis tests for. But 6.1 is all about proportions. Okay, so we'll talk about proportions today. In the next video, which will be on section 6.1 for hypothesis tests. All right. Now, the purpose of chapter 6, 6.1 and 6.2, which is I'll be going over 4 videos. The purpose of it is to give you the complete understanding of how to use formulas for determining both confidence intervals and hypothesis tests. All right. Again, section 6.1 is all about proportions. Section 6.2 is about means. So we're going to cover the same ideas of confidence intervals and hypothesis tests for proportions in section 6.1 and for means in section 6.2. Now, the rest of chapter 6 we will not cover because it's not part of the curriculum in Rowan's Stat 1 course. Now, we did cover difference in proportions and difference in means when we were talking about both confidence intervals and hypothesis tests, and when we were doing simulation in StatKey. We were doing, if you remember, with confidence intervals, we were using the simulated confidence intervals. Let me just go over what that was called again in your book, so there's no confusion about this. And it was called Bootstrap. That's it. Bootstrap confidence intervals. That was what StatKey uses to simulate both confidence intervals and hypothesis, just confidence intervals. And then they use randomization, different types of randomization samples for hypothesis tests. All that we covered earlier. And the purpose of that was just to give you an idea, without all the formulas, just give you an idea of how to construct confidence intervals and how to do hypothesis tests. That was the whole point of all of that. When you get to the final exam, the core piece of the final exam, the only thing that the Department of Math is interested in is testing you on formulas. So typically people will go directly to formulas when they study confidence intervals and hypothesis tests. Sometimes some students get lost in those formulas. So that's why I chose this textbook, the Locke textbook, because they go over all of these concepts first using StatKey, using simulation, so that you don't need to know that many formulas at first. Or you get an understanding of how to create a confidence interval and how to do a hypothesis test, all the steps involved. Then we just slowly introduce the formulas. And finally, in this section 6.1, we complete the idea of the formulas to use. Because we're going to be using, of course, the normal distribution, mostly to construct both confidence intervals and hypothesis tests. And then I'll be introducing a second continuous probability distribution called the t-distribution, which is very similar to the normal distribution, and we'll use it in particular cases. And I'll show you exactly when to use that. But we'll be doing that starting during the next tape. So for this particular session here, we'll deal strictly with the normal distribution. That's what was introduced in chapter 5. All right. Now, in this chapter, I'm going to share the screen with you, and we'll go right to the textbook. All right. So let me see if I can find the textbook here. All right, doesn't seem like it's there, so I have to, fortunately, I have to do some clicking here. Oh, I see what happened. It's like, oh, here we go. I thought it signed me off, but it didn't. So now I should be able to share the screen with you. And let's see, where are you? Here we go. All right. All right, you should be able to see now the textbook. This is section 6.1. And in 6.1, the very first section, it says 6.1-D. D deals with the distribution. In other words, we're going to be looking at the distribution of a proportion. And remember what a proportion is, right? We have a categorical variable, and just like we did in the beginning of the course, a categorical variable, we count the number of people who choose maybe one choice versus another. That was also connected with the idea of a binomial, right? So if we have two candidates for political office, and we're interested, and let's say one is candidate A and the other is candidate B, and we want to count the number of people who are going to vote for candidate A, then the proportion would be the number of people who can or want to vote for candidate A versus everyone who we've asked the questions, right? It's just that proportion. And so we think of that as like a binomial, right? And so the distribution of a proportion is what we're going to talk about here. Now, remember, a proportion deals with a categorical variable, right? And as such, that the counting of the number of people who like one choice versus another, that counting that we do, the frequency distribution that we create, is a discrete random variable. However, if we meet certain criteria, we can actually use the normal distribution to approximate this this binomial. All right, and that's what we're going to do here. We're going to use it as an approximation. All right. So, if you remember, way back when we talked about the central limit theorem. All right, this is for when we are trying to estimate a parameter, population parameter with a sample statistic. And basically, the central limit theorem says that sample statistics often follow a normal distribution if the sample size is large enough. If the sample size is large enough. Now, with proportions, there's a specific thing that we have to do, a certain calculation we have to do to determine if we can use the normal distribution as an approximation for the binomial. That's the whole thing. That's the whole idea what we're going to do here. All right. And I'll show you what that thing that we have to do in about a minute or so. First of all, what we need to do if we're dealing with a sample, if we're determining a, if we're dealing with a sample proportion, and we want to find the distribution of the sampling distribution of sample proportions, we can calculate what's called the standard error. That's the standard deviation of the sampling distribution, if you remember. Now, in the previous chapters, we used the simulated standard error that came out of Stackey to determine what to plug into the standard error. All right, and now we're going to actually use a formula. So this is where the last formula comes in. And so we have to determine the standard error of the sampling distribution of sample proportions. And this is the formula right here. So it's a square root, and what is P? P is the proportion, all right? In other words, if we're interested in the who's voting for candidate A, we count the number of people in a sample who vote for candidate A and divide by the number of people in the sample. That's the sample proportion. So the proportion, that's what we're talking about here, the proportion of people who are voting for candidate A versus candidate B, something like that. Now, P is the proportion, and 1 minus P is the 1 minus that proportion. That in the case of candidate A versus candidate B, 1 minus P would be the people voting for candidate B instead of candidate A. All right, and then there's the sample size. How many people are we asking this question to? Square root of this fraction is the standard error. Now, for example, in the example that we've seen quite a few times, if we know that the proportion of US adults who are college graduates is 0.275, in other words, we know the population proportion, we're creating a sampling distribution to sample proportions of maybe size 200. So every sample, let's say the sample that we actually do has 200 people in it, right? And we're going to ask them the question, are you a college graduate or not? All right, so the probability of, or the proportion of people who are college graduates, 0.275, and the sample size is 200. So if we use this formula here, we just plug in the numbers. So the population proportion is 0.275, 1 minus 0.275 is 1 minus p, and then n is 200, and we take the square root of that fraction, we get 0.032. So that's a standard error, all right? Now, what we know from this formula, and just something I want to bring up that's brought out a little bit later on in this section, is that the standard error is controlled somewhat by the sample size. Notice the sample size is in the denominator of this fraction. So what this means is that as the sample size increases, this is something you should know from arithmetic. You have a fraction and the numerator is fixed, but the denominator is increasing. Our fraction will become smaller. So if we increase the sample size, this fraction becomes smaller and the square root of it becomes smaller. And that means the standard error becomes smaller. And remember, the standard error is the standard deviation of the sampling distribution. So we want that standard error to be as small as possible. That way our estimate that we're using the sample estimate that we're using for the proportion, that estimates population proportion, is a pretty good estimate, right? So we want the standard error to be as low as possible. So the bigger the sample size, the smaller the standard error, and the better off we are in when we create our confidence interval. Okay, and this is an example right here. Okay, and they're giving the example. Suppose and they're using a different example here. Suppose the proportion is 0.225 and the sample size is 50. Notice the standard error, once you take the square root of that fraction, is 0.0612. Notice if we increase the sample size to 200, and we're using the same p, the same proportion, notice it's now 0.0306. It's smaller. So again, the bigger the sample size, the smaller the standard error. That's a good thing. Now, we talked a minute ago about the central limit theorem, and that basically, if the sample size is large enough, then we can assume normality for the distribution, sampling distribution, right? Now, with proportions, if the proportion is close to 0, remember proportions, just like probabilities, run from 0 to 1. And here's a proportion 0.05, close to 0. Notice that when you look at the distribution of the samples for what size here, I guess it's size, I'm not really sure what the sample size is here, probably 10. All right. Doesn't really say, but basically the sample size, if it's not large enough, notice that the sampling distribution here of sample proportions is not bell-shaped. It's skewed to the right. You see it? And the same thing we notice when the proportion is close to 1. In this case, it's skewed left. We want for all the procedures we're going to be doing for creating confidence intervals and doing hypothesis tests, we want normality. We want the distribution, sampling distribution, to be normal. So with a proportion, what's required is the following. And this is what you need to remember. This is going to be asked for both in our tests and also the final exam. We have to do the following calculation. We have to multiply, let's see if I can find it here. See it here, so just give me a second. Let me find it. Okay, here it is right in this section here. Justifying the sample size conditions. This little section in here. Basically, what we do is we take the sample size, n, and we multiply it times p. Now, you might have remembered when we were doing the binomial, n times p is the mean of the binomial. Now, that's what we're calculating here, n times p. And so if, for example, if n is, let's say 10, and p is 0.25, then when we multiply 10 times 0.25, we get 2.5, all right? So anyway, what has been found by statisticians is that when we multiply n times p, the sample size times the proportion, and if the number is at least 10, and also when we calculate sample size times 1 minus p, we find that that's also at least 10. So we say greater than or equal to 10 for n times p, n times 1 minus p is greater than or equal to 10. If those two conditions are met, then we can assume that the sampling distribution for these proportions is approximately normal, approximately bell-shaped. And they show examples right here, all right? They show you here. And they're showing different sample sizes here. Here, let me show you this one right. So here's an example when we have a sample size of 50, all right? And here's when p, and notice that this one right here, notice that, I'm sorry. Let me restate this. Let's look at these three at the bottom here. Okay, there's three different sample sizes here. We have 10, 25, and 200. Okay. And we have, in this case here, make sure I understand this correctly, we have that our proportion is 0.10. So if the sample size is 10, notice that n times p is 1, right? 10 times 0.1 is 1. Notice that's well below 10. And when we plot the sampling distribution, in this case here, we notice it is not normal looking, right? It's skewed to the right. Even when we increase the sample size to 25, notice that 0.1 times 25 is 2.5. It's still below 10. We still see the skewness. But notice now when we have n is 200, the sample size is 200. Notice 200 times 0.1 is 20. That's above 10. And notice that the sampling distribution is normal. So the whole idea here is we want the sampling distribution to look bell-shaped. We want it to look like this. And therefore, when n times p is greater than or equal to 10, typically it will look like this. This is what we want. All right, so that's what we have to determine. We have to calculate those two things, n times p, and also, by the way, n times 1 minus p. And in this case here, since p is 0.1, 1 minus p is 0.9, and obviously it will meet this condition also. N times 200 times 0.9 is 180. Obviously, it's well above 10. You have to do both calculations, n times p, n times 1 minus p, and determine if they are both at least 10. If they are, great, we can use the normal, and we can do all these calculations using the normal distribution, everything that we're going to be doing, all right? So that's the whole idea. So that is, now, on a test, this is something I should mention to you, on a test, it may ask for, let's say we were creating a confidence interval for a proportion, all right, for a population proportion. And you may be asked, what are the assumptions that you're using? Well, there are two assumptions. First assumption, it's the one we always use, is that the sample was acquired randomly. And those we randomly sampled the population. We have a random sample. We always have to state that. That's always one of the assumptions. The second assumption is this n times p and n times 1 minus p both have to be greater than or equal to 10. Both those are the two assumptions, all right? And when I get back and we'd start doing some examples of confidence intervals and hypothesis tests. All right, we'll have a couple days to do that. And then I want to show to you that those are the assumptions that you must talk about. So on the final exam, there's typically a question where they ask about assumptions, all right? It could be confidence intervals, could be hypothesis tests. It doesn't matter. If it has to do with proportions, those are the two things that you have to solve. There's randomly sampled. Of course, it has to be randomly sampled. You have to state it, right? And then you have to say, yes, it's true. It's randomly sampled, and because it's a word problem, and they say it in there that the sample was randomly selected from the population. If that's what they say, then you could say, yes, it's true, right? It's not only an assumption, but it's true. And then you have to calculate the NP, N times P, and N times 1 minus P, make sure they're both at least 10. If they're both true, then you can go ahead and do the confidence interval. All right, now, so anyway, in this section here, they show you how to calculate the standard error. It's very easy. And also they're showing you here how to make sure that N times P and N times 1 minus P is at least 10. And in this case here, when the proportion is 0.8 and the sample size is 400, as you can see, N times P is 320, N times 1 minus P is 80. They're both well above 10. And if they do say up here that it's a random sample, and look, if you read this, Bureau of Transportation Statistics tells us 80% of flights for a particular airline arrive on time. We examine a random sample. There's the randomness. That's one of the requirements, right? So they talk about a random sample of 400 flights. 400 is your sample size, all right? And they compute the proportion that arrive on time, compute the standard error, all right? And the standard error is this, all right? So hopefully this makes sense to you. Again, you can do some of these examples in here just to, number one, let's take a quick look here. So exercises 6.1 to 6.6, this is random samples of the given size are drawn from a population with a given proportion. Find the standard error. So we're just calculating the standard error. All right. So let's actually do an example like this. Let's look at samples of size 50, and the proportion is 0.25. All right, samples of size 50, and the proportion is 0.25. All right, so let's actually stop sharing here and go to the calculator. All right, so N times P. All right, so once again, the sample is size 50, I believe. Let me go back. Let me take a quick look here. Size 50, proportion 0.25. Right. So actually, I'm sorry, I had to do that, and now you can't see the calculator. So let me go back. Sorry about that. Let me share the screen again. Calculator. All right. So the sample size is 50. So it's N times P is 50. Let's do it. 50 times the proportion P, so N times P, 0.25. And notice that's equal to 12.5. And that is larger than 10. We have to calculate N times 1 minus P. So again, 50 times, 50, I forgot to multiply, times, and then parentheses, 1 minus P. And we know what 1 minus 0.25 is 0.75, but we're just going to type it in like this, hit enter. All right. So N times P is 12.5. It's bigger than 10. N times 1 minus P is 37.5, bigger than 10. Since they're both bigger than 10, we can use the normal distribution to approximate the sampling distribution of this proportion, right? Of the sampling distribution for this particular population, right? All right, and it's size 50. That's the samples that we're going to be taking. All right, so we can use the normal distribution. All right, let's go back, stop sharing here. So, and share the book. All right. And of course, we can, all these examples are the same thing. You just take the sample size and multiply by the p proportion, and then you do n times 1 minus p. Okay. And by the way, let's look at 6.4 here. Sample size of 30.27 is the proportion. All right. Sample size 30.27. Down. All right. So let's go to our calculator. And I hope you don't mind me just saying this. I'm going to the calculator. It reminds me I have to share the screen. All right, so n is 30. 30. All right. And then the proportion is 0.27. Oops. Here's an example where we cannot use the normal. Notice that n times p is 8.1. Now, 30 times 1 minus p will be greater than 10. Let's go ahead and do that. 30 times 1 minus 0.27. That's bigger than 10, but both of these have to be bigger than 10, both n times p and n times 1 minus p. If only one of them is bigger than 10, we cannot use the normal. We cannot use the normal for the sampling distribution. And therefore, all this stuff that I'm teaching you in terms of calculating the confidence interval using the normal distribution, we can't use it. We'd have to use something else. And what's the something else? Well, we could use bootstrap. All right, we could use some sort of bootstrap confidence interval like we did before, but we can't use formulas. Here's an example here where we cannot use the normal because the sample size is not large enough, right? Because the proportion is low, 0.27, the sample size has to be sufficiently large enough so that when we multiply n times p, it's at least 10. And in this case, it's not, it's 8.1. All right, so this was an example here where we could not use the normal distribution. All right, anyway, let's now go to the next section. All right, now, here's something new. Here's something new. We know that a confidence interval is the sample statistic, the point estimate of the sample statistic, right? The point estimate of the population parameter. So for example, if it's a proportion, it would be the sample proportion would be an estimate of the population proportion. We've gone over this before. And then we add and subtract the margin of error, right? The margin of error. Now we are breaking up the margin of error into two separate pieces here. Two things that need to be multiplied together to give us the margin of error. There's a z with a star there. I would call that the critical value, right? And I'll show you how to find that. And then SCs are standard error. And what's a standard error again? The square root of the proportion times 1 minus the proportion divided by the sample size. Now, let's scroll down. When we estimate a population proportion using a sample proportion, and we're doing this by creating or constructing this confidence interval, we don't know. We don't know the population proportion. We don't know this p. Right, so that's a little bit of an issue, right? It's not something we know. However, statisticians have discovered that it is okay to replace the p with the actual sample proportion, the p hat. Right, this is something that we've gone over before. That p hat is our sample proportion for the sample that we've got, and it's used, and that's our point, and p hat is our point estimate for our population proportion p. So instead of using p here, we're going to replace the p with our sample proportion p hat. So it's going to be p hat times 1 minus p hat divided by n. The square root of that is going to be our estimated standard error. Right? So our point estimate, our sample statistic, is the point p hat. That's our sample proportion. And then this is the estimated standard error that we're going to use. And the question now is, what's the z star? Right? Because the z star times the standard error is our margin of error. And our margin of error is what we're going to be adding and subtracting to the sample statistic. This is what we've done before. And that gives us our confidence interval. All right, so, and here it is in symbols here. So the other thing we haven't gone over is the z star. All right, so what is that z star? Well, suppose we want to have a 95% confidence interval. Now, it says the sample has 52 peanuts and 48 other nuts, right? So we have a sample of nuts, mixed nuts, 100 mixed nuts. And the sample, if we count the number of peanuts in the sample, out of 100 nuts, there's 52 peanuts. That means the other 48 are other types of nuts. They could be cashews, Brazil nuts, whatever. All right. So what is the proportion of the 100 that, in this case, that are peanuts? What would be 52 divided by 100, right? Or 0.52. That's our sample proportion of peanuts in that 100 jar of 100 mixed nuts, okay? And we want to create a confidence interval for a 95% confidence interval. 95% confidence interval. So, the question is, what is Z star? Well, Z star is going to be that endpoint that we calculate from what? From inverse normal. In other words, we make the middle part of the normal distribution, the middle part, to be 0.95. We've done this before, right? We created a 95% in the middle. 0.95 is the area in the middle. And that means there's 5% left, 2.5% on the left tail, 2.5% on the right tail, right? 2.5% is 0.025. And then what do we do? Well, let's just go back to our calculator. Go back to the calculator, and I'm going to clear the screen. We're going to use inverse normal. We're going to find that Z star. All right, that's inverse normal here. Hit enter. Now we only have to find one of them, the positive one. Positive one, right? So that Z star is going to be the endpoint on the right. In other words, if we create our area in the middle, 0.95, the endpoint on the right of that area is the Z that we want. We want the positive Z. Now, if you remember, the area to the left of that is going to be 0.975. How do we know that? Is because we know the middle area is 95% and the left tail is another 2.5%. And I showed this to you in class. So when we have the area in the middle be 0.95, the area to the left of that endpoint, the one on the right, is going to be 0.975, right? 0.975. Now, the Z is the standard Z, right? The Z score. So we want to use the mean of 0, standard deviation of 1. That's the Z that they're asking for in that formula. Hit enter. And here's our 1.96. We've seen this before. 1.96. Okay. And which is about 2, isn't it? It's close to 2. All right. So for 95% confidence interval, the Z star that we're going to use is 1.96. So let's go back to the book. And notice that they replaced the Z star with 1.96. So that's that inverse normal, the positive Z, all right, the one on the right, 1.96. That's what we're going to multiply times the standard error. So the Z is our critical value. We can call it critical value. In this case, they call it something else, but it is a critical value. And then we're multiplying it by the standard error, and this whole thing, when we multiply these two terms together, we get our margin of error, which is 0.098. So the margin of error is the z times the standard error. And all right. Now remember, in the standard error formula, we're replacing the p hat with the p with the sample proportion, right? And what is it in this case? 0.52. So we're going to put 0.52 here. 1 minus 0.52 divided by 100. That's your sample size. There's 100 people, or 100 nuts in this case, being sampled. Take the square root of that, this whole thing. You get the standard error. Okay? And then multiply it by 1.96, and we get our margin of error. Now, I'm going to show you how to do this with your calculator. All right, this is important. So I want to show you how to create with your calculator the actual this actual confidence interval. Once we add and subtract 0.098 from 0.52, we're going to get this interval here. So 0.52 minus 0.098 is 0.422. 0.52 plus 0.098 is 0.618. So our 95% confidence interval is between 0.422 and 0.618. And the interpretation is that we are 95% sure that the true population proportion of peanuts in mixed nuts is somewhere in between these two numbers here, right? 95% sure, which means if we ran this process of sampling 100 mixed nuts and we ran it over and over again, thousands, millions of times, we would find that 95% of the samples, confidence intervals that we would create from each sample, 95% of those confidence intervals would contain the true population proportion of peanuts, all right, in 100 mixed nuts, and 5% won't. So when we say we're 95% sure, what we're really saying is we're hoping that this particular interval here that we're seeing, 42.2% to 61.8% of peanuts, that this interval is one of those 95% of intervals that do contain the true population, right? Okay, now I want to show you how to create this confidence interval here using your calculator. And it's easy to do it if you follow the following steps. Now, the first thing that you can do is do the z. Find out that critical value. So that's what we did here. All right. I went again to inverse normal, put in my 0.975, 0 and 1 is the mean and standard deviation, and I get this is my standard error. Now, you know that the z is being multiplied by the standard error. So I'm going to hit the multiplication key here. Now notice I haven't written anything down. And now I'm going to do square root. So I'm going to go and do my square root. So second, and then square root's right above the x squared button. Now I'm going to start typing in the proportion. So it's 0.52 times 1 minus 0.52. So I'm going to put that in parentheses. Close parentheses. And then I'm going to divide that by the number in our sample, which is 100 nuts. All right. Now, I'm now multiplying the z times the standard error that's inside the square root, and I hit enter, and that's my margin of error. That is my margin of error. Okay. Now, how do I create my confidence interval? I type in 0.52. I'm going to type in 0.52 here. And I'm subtracting for the left endpoint of the confidence interval. I'm going to subtract from that the margin of error. So I'm just going to scroll up. hit enter, hit enter again. There's my left endpoint, 0.422. And then I'm going to do the right endpoint, 0.52, plus that margin of error. There it is, hit enter. Hit enter again, 0.6179, which is rounded to 0.618 if you rounded to 3 decimal places. And there is my confidence interval, 0.422. Oops, you know what I forgot to do? I apologize. I forgot to share the screen. This is something I keep doing, and I don't need that to you guys. Let me share the screen. Let me start again. Start all over again. So I apologize. So I want to create number one, the margin of error. So I want to find the Z first. This is a 95% confidence interval. Right? So I'm going to use inverse normal to find the Z. Now, 0.975 is the area to the left of the right endpoint for 95% confidence interval. 95% is in the middle. Again, we've done this before. So picture a normal curve where we have 95% of the area in the middle. There's 5% left, 2.5% on the left tail, 2.5% on the right tail. The area to the left of the right endpoint for that interval is going to be 0.975, or we can simply type 1 minus 0.025, because the area to the right tail is 0.025, right? So the area to the left would be 1 minus that. Anyway, we scroll down, hit enter. There's our 1.96, but I'm going to leave all the digits there. I'm not going to round. And then I'm going to hit the multiplication, because now that I have Z, I need to multiply that by the standard error to get my margin of error. So again, the standard error is going to be square root. Now, the sample proportion is 0.52. And I'm going to multiply that by, but in parentheses, 1 minus 0.52. And then I'm going to take the square root of that. Then I'm going to divide by the sample size, 100. That's the number of nuts. Hit enter. And this number here, 0.0979, is our margin of error. Now, to get the confidence interval, once we have the margin of error, to get the confidence interval, we're going to take our 0.52, our sample statistic, our sample proportion, and we're going to subtract, to get the left endpoint, we're going to subtract the margin of error. Okay, so I'm going to scroll up, hit enter. There is my left endpoint. And then I'm going to take 0.52 and add the margin of error. Okay. And the margin of error again is a 0.0979 number. So again, scroll up, enter, enter again. There we go. So our left endpoint is 0.422. Our right endpoint is 0.618. We've found our 95% confidence interval. We're 95% sure that this particular interval contains the true population proportion, somewhere in between these two numbers. That's 95% sure of it. That's true. All right, so that's how we create our confidence interval. All right. So now, one thing you could do, if you have an 83 calculator, I believe, if I'm not mistaken, it's very difficult, if not impossible, to scroll up and highlight a previously typed in number and then hit enter. So one thing that you could do is, once you've created your margin of error, 0.0979, you could actually store that in memory, all right, in one of the letters here. So let's actually go back up. Let's actually pretend that we've done this calculation. We've calculated Z times the standard error, and this is our margin of error. All right, so I'm going to hit enter. Here's my margin of error, 0.0979. So suppose I want to store that, okay, and that way I can use it in calculation. So there is a button on your calculator called STO. It's right here. And you can store that number. So I'm going to hit this button here. And notice what it does. It's the last number that's in memory after you hit enter. That's the number that's going to be stored. And then I'm going to hit the alpha button, and I'm going to store it in alpha in A. Notice A is just above the math button here. There's A. I'm going to store it in A and then hit enter. And now this 0.0979 is stored in A. This is an alternative for you to store numbers that you see on your screen. All right. Now that we know that A is this number, 0.0979, now if we want to calculate our confidence intervals, and this is helpful for those of you with the 83 calculators, you type in our 0.52, that's our estimated, that's our samples proportion. And then we're going to subtract, and instead of having to scroll up, we know that this number here is in the letter A, we just do alpha A. So we're going to take 0.52, subtract A, hit enter, and there is our left endpoint. And then if we do the same thing, to find our right endpoint, we take 0.52 and add A. Oops. Right? There we go. Alpha A, hit enter, and there's the right endpoint, 0.6179. So that's an alternative for those of you, in particular, those of you who use the 83 calculators. If you have difficulty scrolling up and bringing numbers previously calculated down to a calculation you're doing later on, you can just store the margin of error once you've calculated it and into a letter like A, and then use it in your calculations like I just showed you. All right, so there's a great example of how to calculate your confidence interval. All right, so I think maybe we'll try one more of these, and then I'll show you another type of calculation that you're responsible for, right, in addition to calculating the confidence interval. All right, so stop sharing, go back to the book. All right, so we'll do one more example. Okay. All right, so this is called Quebec sovereignty. Quebec, of course, is a province in Canada. All right, and mentions that it's the only Canadian province with predominantly French-speaking population. All right, so the Montreal, I believe, is like Quebec. But there's been a debate over whether Quebec should secede from Canada, in other words, be its own separate country. All right. So in a survey of 800 Quebec residents, 28% of them thought that Quebec should separate from Canada. Now, this is a survey. Not every single person in Quebec was contacted, only 800. So this is a sample or survey of 800 residents. And 28% of those 800 said they thought Quebec should be separate from Canada. All right. So the sample proportion is 0.28. Now they asked another question later on. They said, do you agree that Quebec society is distinct from the rest of Canada? And 82% agree with that. All right. So that's a separate question. So the first one says, find a 95% confidence interval. This is part A. Find a 95% confidence interval for the proportion of Quebecers who would like Quebec to separate from Canada. Right? So we do not know what every person in Quebec feels, right? We only surveyed 800 of them, and we randomly selected the 800. Hopefully that's what we did. Now, first of all, before we use the formula here, we do have to determine if we can use the normal approximation. In other words, can we use the normal distribution to come up with the confidence interval, to construct the confidence interval? Well, what we have to do, number one, was it a random sample? Well, we assume so here. Even though they don't say random, they should have said it, and we assume that it was a random sample. So that's one of the assumptions that we have to determine. And then the second one has to be, does n times p, is it greater than 10, greater than or equal to 10, and is n times 1 minus p greater than or equal to 10? Now, because we don't know what p is, the actual proportion, we have to use p hat to multiply by n and to determine whether it's greater than or equal to 10. All right. So anyway, let's go to our calculator. We'll stop sharing here. So it's 0.28 is our, and 800 is our, what we need. There's the screen. So N is 800. And then P is 0.28. Notice that's 224. Well, that's way bigger than 10, so we're good. And if we did 800 times 1 minus P, we have to do that too. It's pretty obvious that we're going to get something very much bigger than 10 also. All right, so let's just do that calculation. Oops, I messed up the calculation, so let's just go back. All right, so it's 1 minus 0.28. And close parentheses, hit enter. Notice that's 576. So these numbers are well bigger than 10. The normal distribution will work perfectly in constructing the confidence interval. Okay, so that's what, so we can do that. Now, how do we construct the confidence interval in this case here? Well, we already have the information. The only information we need to do any of this is the sample proportion, which is 0.28, and the sample size, which is 800. That's all we need. So now it says a 95% confidence interval. We already know that the Z is 1.96. All right, we don't need to figure it out again. So, but if you want to, you can literally just do it again. All right, just for practice. Once again, we know that the area to the left of the positive Z, that's the right endpoint of the 95% confidence interval, that Z is going to be 1.96, but we'll verify it. There it is. Then we're going to multiply that by the standard error, which is going to be the square root of P hat, which is 0.28, times 1 minus P hat. Okay. 1 minus 0.28, and we're going to divide that by the sample size. And sample in this case, it's 800. 800 people in the survey. Hit enter, and this is going to be our margin of error. All right, so Z times the standard error gives us our margin of error. I'm going to store it in this case in A again. Let's store in A. The way that'll replace what was in A before. Hit enter. This 0.03111 will be in the margin of error that's stored in the letter A. Now I want to create my confidence interval. So 0.28 is our sample statistic, sample proportion, and I'm going to subtract A. There's our left endpoint for the confidence interval, and then 0.28 plus A. That gives me my right endpoint of the confidence interval, but it didn't let me do it. So for some reason, let's do it again. 0.28 plus A. Enter. And there's my right end of the confidence interval. So if we rounded this to 3 decimal places, the left endpoint would be 0.249. Right endpoint would be 0.311. We would say we're 95% sure that the true population proportion is somewhere in between 0.248 and 0.311. Now, let's stop sharing. We'll go back to the other question that was asked. And I guess we wanted a 95% confidence interval. For the question about whether Quebec society is distinct from the rest of Canada. Remember, the sample proportion out of the 800 people who were sampled is 0.82, right? So 0.82 of 82% of those sampled said yes, Quebec is distinct from the rest of Canada. And by the way, here's the confidence interval, and we just again do those same steps again, right? In this case, we would expect the true population, but we're 95% sure that the true population proportion is somewhere in between these two portions. All right. Now, we might want to try a case where we have a different level of confidence. Let's actually try that before we move on to another type of problem. All right, so let's see if we can find one with a different one. Here we go. So let me find one that works. There we go. Let's look at 6.25. 6.25. In a survey of 1,000 US adults, 20% say that they never exercise. All right. Find and interpret a 99% confidence interval for the proportion of US adults who say they never exercise. What is the margin of error with 99% confidence? So, one, they're asking for confidence interval, and as part of the process of creating a confidence interval, we will get a margin of error. So our level of confidence is 99%. I'll write that down. And we have n is equal to 1,000 is our sample size, and 0.20, 20%, is our sample proportion. So we wanted to estimate the population proportion with this confidence interval. And they want us to determine the margin of error along the way, which is, of course, what we do anyway. All right, so let's go ahead and do that with our calculator. We'll clear the screen. First of all, we have to calculate n times p and n times 1 minus p, but I don't think we're going to have any issues here, because n is 1,000. I think the sample size is large enough. And we multiply that by 0.20, that's p. It's 200, well above 10. And then n times 1 minus p. So we'll do the same thing here. And we have to use parentheses for 1 minus 0.20. Now we may know that's 0.8, but just do it anyway. And I made a mistake there. And the mistake I made, by the way, is instead of using the minus sign, I used the negative sign down here. So calculator doesn't like it. So we're going to do 1 minus 3, and we're going to use the minus sign here. Hit enter. 800, well above 10. So we can use the normal. All right. So now that we've met, we can do all of that. We're going to create our 99% confidence interval. So how do we get the 99%? How do we use the 99% to find z? Remember, z is the critical value. It's that z that's multiplying the margin of the standard error to give us the margin. All right. We have to find that first. So again, once again, we're going to use inverse normal. Now, here is where you have to make a little drawing. All right. It might be helpful to make the drawing. I'm going to clear out the area here. We have to figure out what area I'm going to use here. Well, if the middle area is 99%, then what's remaining is 1%. Half of that 1% goes to the left, half of the 1% goes to the right too. So 1/2 of 1% is in a decimal form, and you should verify this with your calculator, 0.005. Because 1% is 0.01, half of that is 0.005. So your left tail is 0.005, and your right tail is 0.005. So for the right endpoint of a 99% confidence interval, where the middle area of your normal curve is going to be 99%, the area to the left of that right endpoint is going to be 1 minus 0.005. I hope that's clear to everybody. You could try it by drawing the curve. And now we scroll down, hit enter. And there is our z, right? Notice it's not 1.96, now it's something bigger. Now we're going to multiply that. So I'm going to multiply that by our standard error, which once again is the square root Now, p hat in this case is going to be what? 0.2. So 0.2 times 1 minus 0.2. Just follow along. And then we're going to divide by the sample size. Sample size is 1,000. Remember, pulling 1,000. All right. Now, this whole term here, the z times this standard error is going to give us our margin of error. Here's our margin of error. Once again, I'm going to store that in A. Store it in A. My margin of error is now in A. And now I'm going to create my confidence interval. This will be 0.2 minus 0.2 is our sample statistic, sample proportion, minus our margin of error, but margin of error is in A. Enter. There's my lower end of the confidence interval. Now 0.2 plus A will give us our margin of error. It's going to give us our right endpoint, right? So now we're going to say with 99% confidence that the true population proportion is between 0.167 and 0.233 if you rounded to 3 decimal places. All right. So what changes with the confidence interval here? What changes is the z. Now, the bigger the level of confidence. In this case, we went from 90 and 95% confidence to 99% confidence. Now, what does the 99% confidence mean? It means that if we ran this process, let's say we have thousands and thousands of samples of size 1,000. Let's say we had infinite amount of money. We could run this sample thousands and thousands of times and create thousands of samples. We would expect 99% of those samples to contain the confidence intervals created from each of those samples. 99% of them contain the true population proportion. Now the problem is, and this is something that I don't know if you would be aware of it or not, because that z is bigger, the bigger the level of confidence, that makes the confidence interval wider, right? And a wider confidence interval is something that actually is not good because it means that there's more variation that's possible for the various samples. All right, more variation there. And we always want less variation, not more variation. So once again, a way to make it narrower, make the confidence interval narrower, is to increase the sample size. So if we increase the sample size from 1,000 to maybe 2,000, then the confidence interval will become narrower. So let's go back to the book. This is just something that you should just be aware of. Back to the book. And let's go back to the formula for confidence intervals. All right, here it is right here. P hat plus or minus that critical value z times the standard error. Remember, the z times the standard error is our margin of error. It should be clear, hopefully clear to you, that if z gets bigger, if the level of confidence gets bigger, z gets bigger. That means this whole margin of error gets bigger. And when we subtract that bigger term from p hat, we're going to get a smaller number on the left endpoint. And when we add a bigger number to the right, we're going to get a larger right endpoint. And that makes the confidence interval wider. Notice that if we increase n, this whole term becomes smaller. All right. When n increases, this whole term becomes smaller. And when it's smaller, and we add a smaller number to p hat, our left endpoint is actually not so small, and the right endpoint is not so small. The confidence interval becomes more narrow, and that's a good thing. All right, so just something I wanted to bring to your attention. Sometimes on tests in the final exam, questions are asked like that. In other words, if we increase the sample size, what happens to the confidence interval? It becomes more narrow. If we increase the level of confidence, what happens to the confidence interval? It becomes wider. Okay, it's just plain old arithmetic. Right? Plain old arithmetic. That's all it is. Now, the last thing I wanted to talk about today is finding what's called the minimum sample size. Now, what do we mean by this? All right. Well, if you were a real researcher, one of the things that you would be doing before you actually did any research, before you actually did any sampling of people or things, is you'd have to figure out how big the sample size should be. Is it just a random process, or is there something that we can do ahead of time to determine what the minimum sample size, so that we get the confidence interval that we are hopefully looking for? In other words, we want to create a confidence interval that's not too wide, all right? And we want to have a certain level of confidence in that confidence interval, right? 95%, 99%, whatever it might be. How do we do that? Well, we know the margin of error is simply z, the critical value, times the estimated standard error, all right? We've already gone over that. That's the margin of error. Now notice that n, the sample size, is in that formula. So if we squared both sides to get rid of the square root and then rearrange the terms using some algebra, we get this formula right here. N is equal to this ratio, z divided by the margin of error, quantity squared, times p hat times 1 minus p hat. This would be a way of calculating the sample size before we actually get the sample and do the research. All right. Now you might say, all right, that's fine. I can calculate z because I know my level of confidence. If I say 95%, I know z is 1.96. And I just found out with 99% confidence, it's like 2.57 or something like that. All right. So I can calculate that with my calculator. The margin of error is something that you can determine up front. You may want your confidence interval to be so wide, right? Now, one thing that you should understand is that when you create a confidence interval and add and subtract the margin of error, that interval now is 2 times the margin of error long. All right. If you're subtracting the margin of error to a number, and if you're adding the margin of error to a number, the length from the left endpoint to the right endpoint is going to be 2 times the margin of error, because you've subtracted it on one side and you've added it on the other side. So you can determine up front how wide you want that interval to be. And that determines your margin of error. So you're going to determine your margin of error up front. You're going to determine your level of confidence up front. The other thing you need is p hat. But p hat, well, that's a little bit of a problem, because you get p hat, the sample proportion, after you've done the research. But remember, this is done before you've done any research, so you don't have p hat. So what do you use? Well, if there were some preliminary studies, sometimes there are, maybe you have an estimate for it, of what p hat could be. And that's what you would use. All right. According to the two statisticians, if you don't have an estimate, then please use 0.5. In other words, if there's no estimate, reasonable estimate for p hat, just put 0.5 in there. And 1 minus p hat, if p hat is 0.5, 1 minus p hat is also 0.5, right? So if the problem that you're looking at gives you an estimate, use it. If not, use 0.5. And then you do this calculation, and then whatever n is, if it has a decimal in it. Remember, this is sample size, so these are whole numbers, right? We're saying 100 people, 1,000 people, 100 nuts, or whatever we're doing. Whatever the sample size is, it's going to be whole numbers. So if you have n is equal to some number plus a decimal, it doesn't matter if the decimal is as low as 0.01. You round it up to the next whole number. So unless you get a whole number when you do this calculation, you just round up to the next whole number, and that is the minimum sample size that you should get. Now you can get more, you can sample more than that and you'll be fine, but you can't sample less than that number of people. So let's just do an example here. We'll show the example and then we'll do one in the back of the book, and that'll be it. All right, so suppose again, now remember we had a poll of 800 Quebecers, right? And we did all of this here, all right? What if we wanted ahead of time, determine how many Quebecers we wanted to survey? And suppose ahead of time we knew that we wanted the margin of error to be 1%, 1 percentage point. Notice it says within plus or minus 1%. All right. So let's read the question here. It's about how many Quebecers should we randomly sample to estimate the proportion of residents who think the province should separate to within 1% with a 99% level of confidence. Well, once again, we know that this is the formula. It's Z divided by the margin of error. And the margin of error, by the way, has to be expressed as a decimal. That quantity squared times p hat times 1 minus p hat. Now, suppose we already did a study and we found 28% of Quebecers. We surveyed 800 of them, and 28% was the sample of p hat, right? The sample proportion. So we could use that as our estimate of p hat here in this formula. So 2.576, that's our inverse normal, and that's for a 99% confidence interval. We just did something like that. Let's actually go back and let's share the calculator again. Okay, and I think if we just scrolled up, you'll see that. Actually, it's not letting me scroll up. Here we go. Here it is. See it right here? Here's a 2.5758. They rounded it to 3 decimal places, 2.56. This is the Z for a 99% confidence interval. We just did a problem just like that. Okay. Let's stop sharing, go back to the book. Okay. That's where they got to 2.576. The margin of error that we want is 0.01. Now, if the margin of error is 0.01, the length of the confidence interval is going to be 0.02. Remember I said the length of the confidence interval is 2 times the margin of error. All right? So I want my confidence interval to be, the length of it to be 0.02. I want my margin of error to be 1/2 of that, which is 0.01. I square that and then multiply it by our estimated p hat from the previous study, 0.28. 1 minus 0.28, and I get 13,377.72. And we're going to round that up to the next whole number. So that means we actually have to survey 13,378 Quebecers to get that sort of accuracy. Now, we may not have that type of money or ability to survey that many Quebecers, but if we want a confidence interval to be that narrow, all right, that narrow, with a 99% level of confidence, we're going to end up with a very large requirement for the sample size, 13,378. Remember, we have to round up to the next whole number. Now, don't pay much attention to these approximate formulas here. I'm not going to require you to learn those, so we're going to skip over that. All right. And then we're going to do one more problem, just like the one we just did. All right. So we want to find a minimum sample size. So let's do one more of that, and then we'll call it a day. All right. So let's see. Probably one of the later ones here probably have that. Yeah, here we go. It looks like it's 6.35. Or maybe, you know what, let's find something else that's a little better. Let's find one that's a better word problem. Here we go. Let's look at 6.39. Advertising a sunscreen pill. An advertising firm plans to have a sample of individuals view a commercial on a sunscreen pill that one can swallow to provide a mild SPF protection throughout the day. After viewing the commercial, each individual will be asked if he or she would consider buying the product. How many individuals should the firm sample to estimate a proportion who would consider buying the product to within 4% margin of error with 98% confidence? All right. So we know our margin of error, okay? It's going to be 0.04 because it says plus or minus 4%. So we'll convert it to a decimal. And we know our level of confidence is 98%. 98%. That means the area in the middle of our normal curve is going to be 0.98, 98%. Now, notice there's nothing in this problem that tells you an estimate for p-hat. Remember, that's part of the formula to determine this minimum sample size. So we're going to, in this case, use 0.5 for p-hat because there's nothing in this problem that's asking us to find it or giving us information about an estimated. All right, so let's use our calculator to calculate the minimum sample size. All right, we'll clear the screen here so there's no confusion. Let's just scroll all the way down here, clear it. All right, now what is the formula that we have to use, right? Now remember, the formula is going to be n is equal to z divided by the margin of error, the quantity squared, times p-hat times 1 minus p-hat, right? Let's actually stop sharing. Let me just show you that formula once again in the book. So this is page 442. Let's just scroll back up. There it is. All right, this formula right here. That is what we're going to use. And we'll go back to our calculator. All right, once again, we want a margin of error of 0.04. We want a 98% confidence interval. Okay, so the z is in the numerator of that fraction, right? It's z divided by the margin of error, the quantity squared. All right, so how do I get my z? All right, so actually what we can do, I'm going to open up a set of parentheses because I'm going to square the z divided by the margin of error. So I'm going to open up a set of parentheses, and then I'm going to go to inverse normal. All right, let's clear that out. Now, the area in the middle is going to be 98%, which means 2% is left. Half of that, 1% in the left tail, 1% in the right tail, right? So 98% in the middle, 1% left tail, 1% right tail. That means for the right endpoint of the 98% interval, it's 1 minus 0.01, 1 minus the area to the right. Or you can look at it as the area to the left would be 98% in the middle plus the 1% on the left tail. So it's 1 minus 0.01. This area to the left, 1 minus 0.01. That's 0.99. This is going to be my z. Okay. Now, oops. I screwed up there. So actually, let's just go ahead and just calculate that first. So we'll go to inverse normal. I hit enter. Now, that's our z. Remember, I have to divide that by the margin of error. The margin of error is 0.04. It says 4 plus or minus 4%, so we have to convert that to. So I'm going to divide this z by 0.04. Hit enter. Now, that is the ratio of z to the margin of error. I need to square it, so I'm going to hit the square button here. Hit enter. And then I have to multiply this by p hat. Now again, I have no estimate for p hat. Remember, for a proportion, I'm going to use 0.5 if I have no estimate for p hat. And then I'm going to multiply that by 1 minus p hat, which is also 0.5. Hit enter. I get 845.6. It doesn't matter what the decimal is. I'm going to round up to the next whole number. And that means my minimum sample size is 846. All right, 846 is the minimum number I have to survey. So let's go back to the book. And let's scroll down. Okay, hold on 1 second. Here it is, 6.39. The answer is 639, I believe I said. Let's just look at the solution. I'm sorry, it wasn't 639, it was 846. 846. Let's just verify that. Let's go back to the calculator. I don't know why I said 639. There it is. 846, right? Round up. This is how I did it with the calculator. And let's go back to the problem itself. Again, this is 6.39 on page 442. Here's the calculation, right? 846 is the minimum number of people that need to be sampled so that I have a confidence interval that has a margin of error for 4 percentage points, and I have a 98% level of confidence. All right, that is it. All right, so hopefully this is somewhat clear to you, clear enough that you can do your homework with this, with the confidence, at least the confidence intervals part of section 6.1. The next time I will continue with this section talking about hypothesis tests with for population proportions. Okay, we'll talk about that and how to use the formulas. Now that we have a formula for the standard error, how to use formulas to come up with our, to calculate this time the p-value. Remember in the past, we used StatKey to come up with a p-value, right? We used a simulation, a randomization hypothesis test, and we were able to come up with our p-value that way. Now we're going to use a formula to calculate the p-value, and we'll run through the hypothesis test just like we did before. This time we're calculating. So we'll show you how to do that next time. And I'll stop sharing. So that's it for today. And hopefully it was somewhat clear to you. At least it was a beginning for you to start doing this. Remember, when I come back from my trip, very first thing I'll be doing is reviewing how to do these again. So hopefully this was useful. Remember, you do have Wiley Plus to do the homework. They have videos in there that will be helpful. You have your textbook. I know this is not easy material, but again, we'll have plenty of practice when I get back. This is just a start, and hopefully you'll be able to know the calculator steps. Now, I have not shown you Microsoft Excel at all. I'll teach you that when I get back for the Microsoft Excel quiz that we'll be doing for confidence intervals and hypothesis tests. I don't want to confuse you more about Microsoft Excel now. I'll show that to you later, all right, when I get back. All right, that's it for today. So I'll stop the recording, and I'll see you next time for video number 2. Have a good night.